didn't tell me in advance.
So please don't dash off to lunch. It should just take a few minutes. Any other announcements? Am I missing anything? Okay, great. So I'm very happy to welcome Vitaly Shmatikov from Cornell Tech, who will be talking with us about what our ML model is hiding. Vitaly is another one of these folks who, every time I hear him speak, I feel like there's a not so good surprise. So I'm looking forward to hearing what he has to say. At least one not so good surprise. Looking forward to hearing what he has to say.
I see.
Thanks.
So you guys got yourselves a good news Vitaly and bad news Vitaly, right? Okay. All right. So thanks for having me here. So today, so this is going to be a very high-level talk. No technical details in it. And there is a reason for that. There are actually like some technical details that I'm happy to kind of share, in the hallways and so on. But what I really want to do is describe a problem, which is, I feel like I kind of stumbled on this problem, and by problem I don't mean like problem as like problematic, as like there is something interesting going on. There is a research problem in all of this. And I'm just trying to get a handle on this. So this is going to be kind of a very high-level attempt to describe what this thing is. And so the title of this talk is What Are ML Models Hiding? And I know in the program it was described as unwanted learning. But that's exactly what I'm going to be talking about, unwanted learning, for lack of a better name. Actually, if anybody has a better name for what I'm describing, like tell me at the end of my talk. All right. So all right, here we go. So I don't know much about machine learning, unfortunately. But in my kind of very imperfect understanding of it, it works something like this. So you take a data set and you put it through some, fancy thing, like TensorFlow, PyTorch, or what have you, and, run on GPUs and whatnot. And out come models, and you use these models for something. Like prediction or analysis of something or other and so on. Okay, that's about all I know about machine learning. But one thing I noticed is that typically when people use this, like, how do they know that the thing is actually working and working as intended? So the question that they typically ask when they do this, what do you think is the question that ML people ask when they go through this process of taking a data set and building a model on it? So what is the main thing they seem to care about?
Test accuracy.
Can I sell it?
Test accuracy. No, it's actually, no, I mean, like, look at your colleagues, from Google Brain. I mean, is this what they really ask? I mean, can I sell it? They have people in the next building to do the selling for them, right? No, they ask like test accuracy, which is another way of saying, did the model actually learn the task that I gave it? Okay? So as far as I can tell, that's what they care about. And that is indeed captured by test accuracy, meaning that they train a model for a particular task, then they take a bunch of data that they didn't use during training, give it to the model produces some results, and they measure if the results are good, and that's test accuracy, and that's kind of how the whole thing works. So, so far so good. What I'm going to try to argue over the next half hour or so is that this question about test accuracy and did the model learn its task well, important as it may be, doesn't cover everything you might want to know about the model. And it certainly doesn't cover everything you might want to know if you care about things like security and privacy and integrity and all these things. That there is a lot that could be happening in a model, both good and bad, that is not actually captured at all by test accuracy and is not even captured by this kind of high-level question of did the model learn the task I gave it, did it learn it well? So the first inkling that there is something more going on in modern machine learning than then is, there is the good news, Vitaly. Okay, so, okay. So, all right. The first inkling that there is more going on than is captured by this notion of test accuracy is something that you guys all know about, that you might have actually heard me talk about this because I've been talking about this for the past couple of years a lot. And this is this idea of leakage from the output of the model. So this is the kind of thing that is not going to, for most of you, is old news. It's the idea that if you look at what the model is producing. So in this case, let's say it's a simple classification model, so it produces some distribution over classes with associated probabilities, that it turns out that very often these models, they behave differently. That is, they produce differently shaped distributions on training and non-training inputs. So that's kind of a very basic thing, that, as you well know, is going to enable membership inference. But one point that I want to make about this is that this difference is not really captured by test accuracy at all, because test accuracy typically is about the likeliest prediction. So the model could be leaking all kinds of information. In this case, it's information about membership in the training set through what it's outputting kind of outside its likeliest prediction. And that does not affect test accuracy at all. And test accuracy could remain high. And nevertheless, there could be all sorts of signal in the output of the model that leak information. So this thing is could be actually, these differences could be exploited. You can actually train an adversarial model to tell the difference, which enables black box membership inference. So I'm not going to talk much about it since I already talked a lot about this, but it kind of enables kind of these things like, you can tell if some, certain images are on the phone, you can tell if certain places are in a location data set. It also kind of provides nice introductory material for differential privacy papers, so all the good stuff. But once you realize that this is going on, you kind of start asking questions. So the first question that comes to mind is that if this leakage, if this just goes, all I'm doing so far is just looking at the output of the model, and I see that even if test accuracy is the same, it could still be leaking information through its outputs outside the most likeliest prediction. But that's kind of black box. All I'm seeing is the output of the model. So the next question to ask is, how about I try to look inside the model and see what it's learning? And by the way, sorry, just to make a point, this question, does model leak its training data through its output in a black box fashion? The answer to that question is actually not captured by any of this. So that's kind of question number one. But now let's look inside the model. And this is where kind of the interesting part starts for me. And this is something that I've been kind of obsessing a little bit over the past year or so, ever since we first noticed this, that if you try to look inside the model and try to kind of understand what did the model actually learn when you applied it to your training data, we discovered kind of all sorts of interesting things. So this is whatever it is. It's kind of like a visual. It doesn't. What I'm trying to say, it's like doesn't matter what the task here is. It's a representation of the features that the model has learned when you applied it to the training data for a particular task. And it turns out that a bunch of these features are actually features necessary for the task that you gave it. So you told it, like in this particular case, the task is to think of it as separating points by color, where color corresponds to a particular class. And you can see that the model has learned it pretty well. That is, it separates these features pretty well. But the amazing thing that was a revelation to me is that in addition to discovering the features that it clearly needs to perform the task you gave it, it also discovered a whole bunch of other features, including features that leak information, that are, like I have to pick my adjective carefully here. It's not that they're unnecessary, because in some kind of roundabout way they might be necessary, but they're certainly uncorrelated with the task that you gave it. Okay? So kind of just to give you kind of an intuitive example for the kind of things I'm talking about. So it turns out that I can train a model on a bunch of facial images to recognize the race of the person. And it turns out that this model also learns if the person wears glasses or not. Okay? Even if wearing glasses is uncorrelated statistically with the person's race, nevertheless, the model in the process of learning for a particular task, it discovers all these other, in this case, facial features, such as wearing glasses that actually can also tell if the person is happy or sad. So it discovers like a bunch of stuff internally that is, again, I have to be careful here, not quite unrelated, but certainly statistically uncorrelated with the task you gave. So, and this is important, because what this tells me is that when you apply a model to a data set, and that's kind of the main point that I'm trying to make today. When you train a model for a particular task on a data set, it's going to learn things. And it's going to learn way more than just the task you gave it. And if all you're looking at is did it learn the task you give it well, you're not actually like asking or discovering what else the model has learned beyond this. It actually has implications for privacy. For example, another thing that we discovered that we can train a model for a generic task like recognizing gender, recognizing race, recognizing if somebody's happy or sad, and yet the model internally learns representations that correspond to individual identities. So it actually learns to recognize individual people in the data set, if there are enough representatives there. So here we have a model that is trained for an ostensibly kind of very generic task like sentiment detection, but internally it has the functionality of a facial recognition model that actually recognizes individual people, which actually has implications for privacy. It also, I feel, has implications for regulation of various kinds. So, and this could be demonstrated very concretely using transfer learning techniques. So we have these experiments that basically show that you can take a model that was used originally to like infer gender of the face, and you can derive a model that actually infers the race of someone from that model. Or the model is used to infer emotion, and you can actually turn it into facial recognition models. And this is not just for image detection. It also, the same effects we observe in NLP models. So for example, you can take a model for inferring sentiment of text, and you can use its internal representations to create a model that infers authorship. Yeah?
Just quickly, so what you're saying with the transfer learning, you don't need the training data for the second?
No, you don't need the training data. So imagine like the training data is gone, all you have is the model trained for this task, and then I turn it into a model for this task. So, yes?
But you get training data for the new task?
A little bit. But not enough to train a good model. So I take a little bit of training data for the new task. I can train a really crappy model on that. But that data plus the old model gives me a good model for the new task. Now, at this point, I have to kind of be very careful about what I say. Because when we first discovered this, I was all like, kind of peeing myself with excitement and kind of telling everybody about this. And like ML people are like, like everybody knows this, right? Actually, I feel like whatever research I do, it's like people's reaction is everybody knows this. So yeah, well, that's, not a happy thought. But here is what they mean by everybody knows that. It is true that like if you look at ML literature, and like these are not people like me, like these are professional ML people who like train ImageNet models and kind of become rich and famous off of that. Like they do know that there is like that models discover things that are in some sense more than you ask them to discover. So like you can take a model trained for ImageNet, and for those of you who don't know what it is, this is kind of a very rich kind of image analysis, image classification task. And you can use that model using very similar transfer learning techniques to perform all other kinds of image classification tasks. But that is not quite what I'm talking about here. Because, of course, if you train for ImageNet, and training for ImageNet meaning training a model that can recognize like thousands of different objects in the image and like classify scenes in a very refined way, I mean, it's not surprising that you can use that model to solve other image recognition tasks, because in some sense, this is like learning in general, like computer vision. Like learning ImageNet is almost like, you know, kind of human level perception of what's in the images. Another effect that people have observed is that if you trained for a coarse-grained task, it actually learns to recognize finer-grained versions of this task. Like, for example, if you teach a model to recognize monkeys, it doesn't just learn to recognize monkeys. It learns to tell, like, I don't know, like chimpanzees from like macaques or something. But again, this is like finer-grained version of the same task. The effect I'm observing here is different. I'm learning for a very simple task. I'm not training ImageNet models. I don't have enough GPUs in my lab to do that. I'm learning, like, these are binary classifiers, like male or female. This is a very simple task. And yet, the representations that the model is learning turn out to be sufficient to perform uncorrelated tasks, other tasks that are actually not a finer-grained version of the task I trained for. I trained for one task, and then I can use the model to train for an uncorrelated task. So that's the surprising thing here, is that I'm not trying to solve the general vision problem. I'm using this model to train for very simple things, and yet, in spite of that, inside of them, they end up discovering this very rich representations, and they extract generic features that are actually useful for all sorts of other things. It's as if, like, no matter, like for these tasks, like kind of no matter how I train, the only way to be training successfully is to actually discover kind of general features that are useful for all sorts of images. Mm-hmm. Yes.
Why should I expect that the fact that the second task is uncorrelated with the first task to suggest that you shouldn't be learning those features? So if like chimpanzees and macaques look very different, then the features that are relevant to recognizing chimpanzees and the features relevant for recognizing macaques might be very different. So recognizing monkeys or primates would naturally give me a way to recognize chimpanzees, to distinguish chimpanzees from.
Yeah, maybe that's what's going.
Uncorrelated matters. Or like Emily Dickinson and Ralph Waldo Emerson have very different types of writing. So sad Emily Dickinson reads very differently than sad.
Okay, so there are two questions in what you ask: why this matters, and why this is surprising. These are different questions, right?
Agreed. I'm asking why. It sounded like you were suggesting it's surprising. I'm pushing back on that.
It's surprising to me,
Okay.
and so far I have not been able to find like any evidence anywhere that this has been observed. That learning for a simple task results in the discovery of generic features that are useful for all kinds of other tasks. I haven't seen this, but I guess it's not surprising. So yeah.
Why do you call it a simple task?
What?
Why do you think that this is a simple task, distinguishing?
Maybe it's not a simple task, okay?
Can I tease that out?
Yeah.
Like when you say gender and race, right? You're like, you said these are not correlated. Which, like, that's a crazy statement from my perspective. Like the ways in which we construct identity, right? Like, I think maybe if you were saying that if inferring race is a simple task because you've defined it as looking at the gradient in people's skin, but we know when we're looking for quote-unquote race, which is a social construct, that the models are learning lots of different things that are more subtle than that, and that the identification of race differs in relation to gender, right? And so, like, I think just to push on that point a little bit, like the way in which you've constructed these things as not related is, and I would say the same thing about emotion and identity.
Okay, good. So let me try to answer all of this kind of in one ramp. So that's why I have to be careful by saying things like, I used to say things like unrelated, and then people pushed back in exactly the way you are now. So uncorrelated just means that in the data set, like, if you look at label on the image for race and label for gender, there is no statistical correlation between these labels. That's all it means. It's a pure like statistical statement, is that like, you know, half are labeled as men, half are labeled as women, and that's all it is. Okay, so you can so it's not a statement about like constructing identity. I'm not making a social science statement at all. It's just a pure mathematical statement about the distribution of labels in the data set. Okay, but it is really but here is what like I feel is really going on, and this is to answer the question about you know, why do I say it's a simple task? So that's the point I'm trying to make, is that apparently it is not a simple task. That in the process of learning for this binary classifier, the only way to learn it is to discover, to sort of perform full-on facial analysis and to extract the relevant features that now enable the model to do not just the task you trained it for, but all sorts of other tasks. And I do know this because there are techniques that come from bias, from kind of biased literature, kind of, you know, FATML community, for censoring representations. Okay? Censoring representations means that you artificially sort of during training try to prevent the model from making decisions based on race, for example, or based on gender, or based on whatever prohibited attribute. And these techniques could be used to try to suppress the model and prevent it from learning things you don't want it to learn. And what do I observe empirically? That if you try to prevent the model from learning one of these things, it's not going to learn others. So the only way to prevent it from learning these concepts is to prevent it from kind of learning, performing like facial analysis features or text analysis and so on. And in that case, it fails at all tasks. So the point that I'm trying to make, which I mean, to me is surprising, but maybe again, it's not surprising to people who actually know about this, is that these properties that you might want to learn for, they come in bundles, okay? As in like, you either learn all of them or you learn none of them, okay? I'm kind of simplifying it a little bit because, I mean, there are certain trade-offs there, but that's kind of intuitively what's happening, is that either you kind of, in case of image analysis, perform full analysis of like faces and then you learn everything there is to know about the face, or you learn none of this. That there is no such thing as a model that, let's say, learns if people are happy or sad, or if the face is labeled as male or female, without learning all the other things like race and if the person wears glasses and stuff like this, including even facial identities, potentially. So that's the point I'm trying to make. Okay? Yeah.
Just a short technical question. When you talk about taking a model that infers emotion and you transform it to infer identities of people and images, the training set that you use for the second test is different people or same people?
Same people. Same people. Same people. But it's going to be harder to do with different people. I mean, but in this case, it's same people. Now, here is I'm really gonna go out of my kind of comfort zone and talk about like regulation and whatnot, but I will. Okay, so there is this thing called GDPR out in Europe somewhere now, and I counted using grep. It mentions the word purpose 261 times. It says that when you do processing of data, the purpose, for multiple purposes, consent should be given for all of them. Of course, these days, data is going to be used for machine learning. That's what people do with data these days. And looking at this whole picture, like, what exactly is the purpose? Like, if you train a model for a particular task, but in the process of training it for that task, you are, whether you want it or not, actually training it for hundreds of other possible tasks. Or at least it could be usable for those other tasks. What is really the purpose of the model? So I feel this is going to be a challenge for people who are responsible for like disclosing purposes to users and obtaining consent from them, explaining to users that, look, I got this model and I trained it, so I'm only going to use it for purpose A. Oh, and by the way, that very same model could be used for all sorts of other purposes, and maybe it is in some sense being used for those other purposes, because maybe in the process of like doing this like neutral thing that I gave you, it actually happens to be recognizing your face and recognizing all kinds of your attributes that, I don't know, you might or might not be comfortable with. So I don't know how all of this is going to work with purpose. I mean, this is not kind of my problem. This is somebody else's. But I just want to mention this because I feel that this idea that you can take a model trained for one task, and because it has implicitly learned all manner of other things, you can repurpose it very easily for all sorts of other tasks, even if the data is no longer available or the data has been erased. This is going to be a challenge. All right, so
How is that for you different than in the past when we would analyze data, publish a result, and the next scientist takes what's learned or the results of that paper and builds on that? I mean, this kind of, repurposing that you describe here doesn't seem to me be confined to this particular setting, but it...
Yeah, maybe it's not. I just feel that it's very hard to tell. Like, I don't even know how to define a purpose of an ML model. Because the same, yes.
Just that, so a video surveillance camera. You can use it for many purposes.
Sure.
This isn't a problem that is unique. When we think about describing the purpose is like more at a socio-technical level. How's the organization using the technology? It's not describe every purpose that the technology could be used for, right? So I agree with you that there may be some interesting things here, but most technology kind of has multiple purposes, and so the way in which we think about purpose is a description of how it's being used, not what it's capable for.
No, it's not about, like, here is an important difference. I'm not saying what these models are capable of doing. I'm talking about what they're doing. I mean, they are actually learning things.
I understand.
So it's not about potential users of this. Yes?
Still, just to pick up on Peter's point, it's still like, we don't say that you have to limit what you're building to only perform one possible function and it's prevented from doing anything else at a technical level. We're saying whatever it is that you use this data to build, when you're actually making decisions, you can only use it for this particular purpose.
So, yeah, I mean, this is the thing that comes up all the time. So, and this is kind of where there is this disconnect between bias and privacy comes into the picture, so to speak. Typically, when people do censoring of models for bias, they only care about the last layer of the model. As long as the decisions you're producing have the right statistical property, like no disparate impact or whatever, I don't know, 13 notions out there apparently, you're good, okay? However, I feel like what these models are doing, like maybe the decision has no bias, but I don't know how comfortable people are going to be. Is like, you know what, I'm going to follow inside the model different decision paths. I'm going to make decisions one way for white people and a different way for black people. And then actually my decision, my final decision is independent of, turns out to have the right statistical property, but inside the model I'm doing different things for different races. Is that okay or not? I'm not the right person to answer that question, but I do suspect that if it turns out to be the case, lots of people are not going to be cool with that. That's all I'm saying. And in some sense, what these models are doing is some of that, as in they actually do perform different. So you don't think?
I mean, there's already an active discussion about, so you can take the risk recidivism software debates, right, about whether or not you could have different rules for different genders or different rules for different populations, et cetera, and an understanding that sometimes the only way to meet some measures of fairness is actually to consider, right? Mm-hmm. And so, yes, how models use information about race, gender, age, all of these things may be super important, and I think merit discussion, but the question about whether or not they're viewed as good or bad is a separate question. But I do think understanding how they're used can be really important.
At the very least, it seems like there is a consciousness that, like, if you are intentionally using features like race or something in some decision, you should actually know you're doing that.
I completely agree.
So nothing else that you should. Right, there's a requirement to understand like the process that's going on, and with these complicated models that are just represented as a list of weights, it's not obvious that that's easy.
Right, and it's not just about the output, that the reasoning matters.
Okay, if it's not just about the output, then I would argue technically that for many of these models, there is no way of eliminating race, there is no way of eliminating gender from their inner workings, because in the process of arriving at their decisions, they will consider them. Because if you prevent them from considering, they no longer learn.
Completely agree.
Sorry, I didn't want to get I put this out there to kind of establish a connection. I'm not trying to say like good or bad, this is not my area of expertise. The only point I'm trying to make is that when you train a model for any one of these tasks, it ends up learning all of them effectively. That's the technical point that I'm making. How to feed it into this picture of like regulation and ethics and so on, you guys are much better equipped than me. Yeah.
So are you seeing experiments showing once you try to censor out race or gender that every single task?
Not every single task, but for certain, well, I don't know how to quantify all possible tasks, but we have these groups of objective functions that if we, like for example, if we try to censor for race, it no longer learns gender, or it no longer learns if people wear glasses, those types of things.
With the same kind of transfer learning setup?
No. Sorry, this is not with transfer learning. I'm just saying, I'm going to take a model trained as a gender classifier. Okay, I'm going to look at its representation. It's clear that its representations leak race. I'm going to apply censoring techniques to prevent the representations from leaking race. The accuracy of gender classifier goes down almost to random guessing. That's it. That's the point I'm making. There is no transfer learning there. It's just trying to regularize representation so that they don't leak race, prevents them from being discriminative on gender. That's all.
It doesn't say that there isn't a way.
It doesn't say that there isn't a way. Although I feel that there isn't. I feel like for precisely the reason that Good News Vitaly said, which is these seemingly simple tasks are actually complex, that maybe to actually learn, race or gender assigned correctly, you actually need to extract low-level features, assemble them into facial features, and perform full-on face analysis, which will actually enable facial recognition. And there is just no other way of accurately recognizing race or gender. It would be very nice if there were a simple way of doing it that doesn't pull in all this other crap. But so far, there doesn't seem to be.
I'm just trying to wrap my mind around that statement. Because it seems like if you trained on a set of images consisting of only one race, then you could learn gender without encoding race.
That's a beautiful thing. So that is what we thought, and the models trained, I should have mentioned this, is that even if you have certain properties not represented in the data set at all, the model still learns to recognize them, which goes to this point of it's actually extracting low-level facial features, okay?
Can you give an example?
An example? Sure. You can train a model to tell Caucasian and African American faces apart. That model turns out to be capable of recognizing Asian faces, even though Asian faces are not represented in the training dataset. It shouldn't be surprising at all. Now okay, first you tell me there is nothing surprising here, and then you're all sitting here, oh, what? But it's not surprising. If the model is extracting low-level features, these low-level features are discriminative, not just for the things represented in the training dataset. They're discriminative for all different types of faces. Okay, that's the point that I'm trying to make. Maybe I should have started from this. These models, yeah?
Just a very basic question, is this like, are these always computer vision tasks? Are we always
No, for language I can do the same thing.
But it's
Yeah.
end to end. Like, we're not using engineered features. This is always.
No, not engineered features. No. If I were using engineered features, that's another reason people tell me there's nothing surprising there. You're using SIFT features, and of course they're generic. No, I'm not using SIFT features. That's the whole point. That's what I'm trying to say, is that I train it for a binary classifier, and it learns the equivalent of SIFT features.
Which was interesting. I'm curious if like you could observe anything similar when you're using engineered features.
We haven't tried with engineered features. No. Let's see. How much time do I have here? Okay. All right. Good. So let me kind of move on real quick here. Okay. So this idea of like, I don't know how to call these effects. Like, I've been using unwanted learning for this, but like, it's not unwanted, unintended. I don't know. If you have a good adjective, you know, and end up using it, like, I'll give you, I don't know, $10. Okay. What was I going to say? Okay, so it manifests itself in all sorts of other ways. So far I've been talking about kind of this unintentional leakage and things that arise unintentionally. Of course, you can do the same thing. You can exploit this to artificially introduce things into the model. So there is this thing that I actually like a lot, but apparently nobody does, with like backdoor attacks, where you can sort of introduce a backdoor into the image so that when I wear these glasses, I get misrecognized as someone else. And again, this works much better than just data poisoning, because you sort of, without having any impact on the accuracy on the main task, you can introduce additional tasks in the model, and the model still does them well. This matters in federated learning, where the models are assembled from multiple models and stuff like this. And this is actually very hard to detect. So this is kind of another angle on this, is that you cannot tell by looking at a model what task it's performing, okay? Maybe that's kind of an obvious point, but even if you know what task it was trained for, it's very hard to tell by looking at the model that it doesn't actually also like perform all sorts of other tasks, or that it didn't learn also all sorts of like other things. This leakage, okay, I'll skip that. This leakage from internal representations is a problem when you get like white box visibility into the model, because if you, like for example, again, in federated learning and distributed learning scenarios, you don't get to see the final model. You see like snapshots of the model over time. And what you see, even in that setting, is that in the top layers of the model, you see these features that are relevant to the task you trained the model for. In the lower layers, what you see is all kinds of like unintended features that leak information about training data. Like, you can't see it, this picture is too small, but this is a model that was trained to like separate triangles and squares, which you can see it separates pretty well. But here it learned to separate by color in the lower layers, which is another example of performing an uncorrelated task that's unconnected. Well, unconnected is not right. Uncorrelated with the final task, and yet here the model is clearly learning to do this. All right. So what am I trying to say with all of this? So remember, I started by saying that when people look at models today, they ask if the model learned its task well, typically measured by test accuracy. So what I've been trying to say is that this doesn't answer the question of what else did the model learn. So because in addition to the task you gave it, it could have implicitly or explicitly, intentionally or accidentally learn all kinds of things that are not captured by its main task. It could have memorized its training data and leaked it. It could have discovered features that are uncorrelated to the task that you gave it. And by the way, you're right that uncorrelated doesn't mean not useful, however statistically uncorrelated. It could actually learn privacy violating tasks, like, you know, you trained for a generic purpose, but it learned to recognize people's identities or authorship of texts and stuff like this. Or it could even be abused to kind of incorporate some backdoor functionality, incorporate an artificial task that somebody put in there to cause it misbehave in certain ways. And None of these things are captured by measuring the model's test accuracy. So if all you look at is test accuracy and test train gap and kind of conventional metrics of model quality, none of them, like these effects of unwanted, unintended learning, they do not manifest there. So if we want to understand what models are really learning, what they're really discovering about the data and about us and stuff like this, then we need to take like a deeper look at this, and we need metrics for that. That conventional ways of doing it aren't going to do it. All right, so let me stop here and yeah, go to questions.
Should we hold questions and let the discussants?
I just had a.
Oh, oh yeah, there is a dedicated embarrasser, right?
No, it's a clarifying question. When you performed these experiments, did you go in and say, we're going to see if the model, like how did you discover that this model was learning other things besides? Were you like taking pot-shot guesses to say, oh,
by taking guesses, okay. So how do we know what to look for?
Yeah.
Yeah, by taking guesses. I mean, it came out of, like originally we noticed this in the context of this federated learning, but that's a little different because in federated learning you kind of get this, it's kind of hard to explain without going into technical details. You kind of get like updates to the model based on small like batches of data, and there we observed that these updates leak information that is like, but the updates are directly based on the data, so it's not very surprising. And then we asked ourselves questions. What if we take a trained model and all these things that are leaked by updates, maybe they're leaked by the final model, and that kind of informed our search, but in terms of coming up with tasks to test for, this is just, things that look plausible and that I could arguably sell as privacy violating to, some skeptical reviewer or two, but yeah.
I'm sure there are other questions. Maybe let's hold them until Sophie has a chance to say a few words. Thanks.
So, sorry, I'm not, like, procedurally, what happens now?
Procedurally now,
you leave the room.
Okay, do I sit down? Okay, all right, okay, that sounds good.
You'll be back up though to answer questions in a moment.
Who gets the mic?
You get the mic, and actually there should be a freestanding mic.
Oh, sorry. I'm still mic'd up.
No, you're still mic'd up, and that's good, and there's another one coming. Excellent.
Thank you. Can you hear me?
Yeah.
All right, so I guess somebody's bad news is somebody else's good news, right? So every time that Vitaly speaks, I guess I feel that whatever we as theoreticians conjecture could be wrong, he actually finds a way to show that it's going wrong, right? And it's a way for us to convince people that what we're doing is useful and indeed it is a problem. So another way I thought that this would be a good news. So when we talk about synthetic data, so what bothers me a lot is, so suppose we think of some uses of the synthetic data and we say, well, okay, let's generate it in such a way that it's useful for this thing, but why would it be useful for other tasks? So if indeed there is a formal way to say that these tasks are somehow correlated, right? So then indeed it would be useful for other tasks. Right, so it's useful for one thing, it's also useful for other things. So it is very interesting that Vitaly is uncovering these things that somehow many useful tasks could be correlated in some intrinsic way. So this is one point that I wanted to make. So another thing, so of course as a theoretician I want to ask, so how can we model it formally? So what's going on here? And maybe in particular, so some of the things that are here on the slide, can they be ruled out if we use private algorithms? So if we use differentially private algorithms, the models are differentially private in some way, but of course we think in many cases about differential privacy of the outputs. But there is something else going on here. So there's some internal state. So how do we ensure, maybe we should be trying to ensure that some internal state is also differentially private. And we have models, let's say, for local algorithms, right? So But maybe there's something in between there. So the model that's getting trained continuously, maybe after every stage, its internal state should be differentially private. So is there something interesting going on there? Can we model it? Is the model going to have strictly less power because it's differentially private or not? So another thing is, okay, Vitaly says, I guess as we all discussed, so that we cannot train for certain features without training for other features. Can we actually formally prove that there is no way to train it? It's not that these methods don't work, but can we actually prove that there are features for which, if you train for those features, you also have to train for other features, right? Okay. Anything else I wanted to say? Oh, another thing is actually testing or learning for privacy or kind of attributes that we want, right? So is it possible to actually test that the program is doing or the learner is doing what you hope it will be doing, that it's private or maybe it's preserving some other things that we're worried about?
And now we can open the floor for questions. You're back on. Yeah,
Thanks. Those are good questions, by the way.
Yeah, actually, first, if you have some responses directly.
No, this is it. I mean, this is, I think these are excellent questions. Because unsurprising as it is, this idea that you cannot learn A without B, or that the only way to learn A is by discovering a bunch of generic concepts that actually enable all kinds of learning. I feel it's a very powerful idea. And even though people react to it, what's surprising here, I've never seen it even explained clearly anywhere. Yes?
So I wanted to slightly push back on this idea that kind of people are only looking at whether the model learned the specific task. So kind of face recognition is the perfect example, right? So how do people train face recognition models? They train them to kind of recognize particular individuals in the training set. And then lo and behold, when you kind of take the embedding layer, then it can do kind of in the wild face recognition.
Mm-hmm.
So it's not, and no one says, okay, we just care about whether they recognize the celebrities that we trained on. It's obvious that the eventual goal is different.
Yeah, well, I mean, but you're talking about, in this example, that's just generalization. So you want the model to generalize.
It's not quite generalization.
No, she's saying that the embedding, if you sort of shave off the last layer or two of the network, you can retrain the last layer or whatever.
No.
That's right. That's transfer learning. When you retrain.
I mean, you get that last embedding layer, right? That gives you an embedding.
You get that last embedding layer, and you just calculate the difference between the two embedding for my picture and another one of my pictures. And if this distance is small, then kind of it tells me, so there's no retraining.
No retraining, but you're changing
then
the
it's not
last
transfer
part
learning.
of the network because now there are more people. Right?
No, she's not changing.
No, she's just using a different classifier. In fact, implicitly using a different classifier on top of the.
Just sticking a different.
Using a nearest neighbor
different,
instead of the original one.
You're doing
it's
a different
transfer learning,
thing with the last
just standard one.
Okay, I think it's a semantic difference.
This you're right. I mean, I think now I think I hear what you're saying. You're saying that the representations that are learned are more general than the task that you gave. Yes, I guess that's what I'm saying. What's amazing to me is how much more general. Sure. I don't know what's the procedure here.
You pick.
So now trying to wrap my head around this. Is it specifically that, let's say you're trying to recognize faces, and then you learn that the images have eyes, noses, and a mouth. That's not surprising, maybe, depending on your algorithm. But if all you want to know, does this image have an eye in it? And then somewhere in the model or somewhere in this network, you're learning to recognize. That's the surprising thing.
Right.
I mean, do you want to distinguish between these two types?
I don't quite know how to distinguish it, okay, because if you think about this, maybe there is no difference. Maybe to learn to recognize that there is an eye in the face, you need to know this is a face, you need to segment it, you need to find the features that segment the face into eyes, nose, and mouth, and perform all that processing just to recognize that there is an eye. Once you've performed all that processing, you're doing full-on facial analysis, meaning that yes, you're going to have yourself a facial recognition model because you will have to extract the same features that a facial recognition model is extracting just to do a thing as simple as determining if there is an eye in it. So, but the surprising thing to me is actually it's again goes back to what Good News Vitaly asked, right? Which is there are maybe no simple tasks here. Is that the only way to do even simple tasks is to do exactly, well, not exactly, but to extract general representations that are useful for all sorts of tasks. That there are no shortcuts here. That's one maybe somewhat surprising part, which is maybe a little bit more surprising that when I do facial recognition for a particular group of people, it has to extract facial features that turn out to be useful for recognizing even other people. Well, I'm not saying, I'm not even doing facial recognition. I'm doing something much, coarser grained, and yet it still discovers features that are useful for facial recognition. So.
I mean, the way I'm thinking about this is like, we often think of like overfitting as degrading real-world performance, but actually it's sort of weird. We're saying it's like, you can kind of think of this as like profound overfitting that then makes what the model has learned actually much more general, applicable.
Right. I don't think overfitting is, I mean, first of all, I don't know what is the technical definition of overfitting, okay? So, but it's hard for me to think of this as overfitting because it's not, what?
This is learning, not overfitting.
This is learning. I mean, as in like, let me come back to this example that now I'm thinking I should use more often, how it learns to recognize the feature that is not represented in the training data set. That's the opposite of overfitting. That feature is not even in there. So how do you mean, like how do I overfit by learning to recognize something that is not in the training data set? This is just showing kind of like how general the learning is, that the things that it extracts are useful for things well beyond this is anti-overfitting in some sense.
This is why I'm trying to kind of wrap my head around it in this way. I agree kind of, but what I'm saying is like, on the process of trying to generalize well with this one particular task, it's sort of like discovering a bunch of stuff that is actually maybe not particularly like strictly necessary for that task, which, I can think of as being like weirdly saying like, it's going to learn all the stuff which is like peculiar to this training set, but somehow still like doesn't really affect the ability for this ultimate model to generalize well with respect to that text. And this other stuff that it learned is going to end up being useful with respect to other tasks.
Yeah. So now I'm thinking like, remember I complained how I don't have a good term for this. Maybe overlearning is actually a good description of what's going on. Whoa. There are like.
Keep going.
Let's go left to right. Is that okay?
Yeah. Your left. Yeah.
My left. Sorry.
Yeah. So I'm curious in these examples, how many parameters of these models are there compared to like what is the? I'm looking for.
Right. So
I want to know how many the size of a learned model compared to the size of the training data set.
Good. So this is a long conversation I can have about this, so I won't bore everyone. So yes, so like if you really over-parameterize the models, you can, like this phenomenon is like amazing, right? It's basic.
Does it happen more is the question. Like, I'm curious.
It happens, it's much worse in over-parameterized models, because over-parameterized models, it's going to do everything. It's going to learn all kinds of things, all kinds of representations.
Learn or memorize?
What's the
Yeah,
difference?
sure. It's maybe not get into that.
Yeah. But it is over-parameterization. Like these experiments work much more beautifully with over-parameterized models. Of course, that's a little bit stacking the deck in our favor. So when we do the experiments, we try to kind of take the model like from the literature, which is like that is maybe still over-parameterized, but not artificial over-parameterized. But I can make everything here much worse by like dumping like 2 more layers on top of it and making it like wide. Okay.
The reason I ask this is that like I have a very hard time imagining a linear separator that was trained to learn gender is going to do the same.
True, but the linear separator is gonna suck at recognizing gender.
Yeah, but
Yeah, well, but again, let me come back to good news Vitaly here. This is very deep. It's like maybe Rick. What?
I'll have to officially now change my last name.
It's.
I think good news should just be your.
Yeah, it's because you actually weren't even here when that joke was made. So yeah. So but. Like this thing, like maybe learning gender, like really learning gender, requires actually like learning everything you can about the face. So there is some deep meaning in that statement.
Have you done anything where you condense the models?
No, maybe we should. That's actually a good point.
Right, or like compress.
All right, let's move on. Yeah, sorry, I know you've been heading.
So this is
Oh, sorry. It's.
I'm fine.
Go ahead.
Are you sure?
Left to right.
Yeah.
Okay, so another way of looking at it is to say maybe all this data that you're looking at is really in a very low dimensional subspace. So those features that the CNN picks up on is pretty much the same whether it's your face or my face or Brad Pitt's face. And there were no other people in the database. So maybe that's all it is, and if you added a little bit of noise to all these features to make it private, you would possibly lose. I'm adding 2 questions here, so possibly lose all utility in that sense.
Yeah. Yeah, I don't know. This kind of goes to the deep question of what is it that these models are really picking on, okay? And it takes somebody who knows, much more ML than I do to
Right, there's some work
answer.
on CNNs that can now theoretically understand how close that lineage is.
That's right. I'm not the right person to even like start answering that question. But I think it's a very meaningful question to ask. Just not of me. Sorry. Let's. You had a question.
So, so this is a thought. I mean, it looks like this may have some implications also for the consequences of limiting the type of information, or the type of data that we feed, that we feed these machines, right? That if we set limits, they will learn less, right? And so that we're paying, that there is some cost in doing this, and this is something that we do often, due to regulation, right? The type of invasion to privacy as an example, and then maybe we are causing some harm, distorting the.
But I see where you're going with this. But what about this? What if these things that you want to learn come in bundles? What if there is no way of learning what you really want to learn? Like, how is data limitation going to help?
No, I'm actually, I'm actually looking at, I'm listening to you, and I'm hearing regulators saying, for instance, we want, for cybersecurity purposes, we really need to collect all the data because we need to detect some, cyber attacks. And we use machine learning for that. But we care about your privacy, so we are going to ensure that some of the data is not going to be available. But there is a cost for that, right? They can't really they can't really apply these systems if they.
I see, sort of that way.
We're going to black out, particular data because we know the.
Yeah, I don't know. I mean, what this means for regulating these things and like limiting.
But you can't set limits, and or that there is a cost that is associated with setting limits if there is some sort of learning that is out there that you cannot really measure, or could you? Is there a way to actually measure everything that is being lost, like through, for instance, the transfer of net learning.
Well, I don't know how to answer that. Other than, as far as I can tell, there isn't even a way to measure everything that's learned. So it would be strange if there were today a way to measure everything that's lost by limiting learning in various ways. So I don't know. Okay, so I guess Deirdre.
So the examples that you were working with are things that while you kind of, initially said simple, you then admitted they're complex things.
Oh, they're simple in terms of the objective function. So.
Yeah, okay. But I'm wondering, so for example, if I wanted to train a model to recognize people with glasses, right, whether or not we would be able to limit.
That's one of our examples.
Right, and even there but if you prohibited it from learning some set of things, for example, about protected attributes.
That is one of our examples. Is exactly like.
Goes down.
That's like this example, learning if somebody wears glasses, like that binary classifier is actually one of our most prominent examples.
Yeah. And so when you then said you can't learn these other things, the performance goes down steeply. So I guess another models are sloppy, right? I do think this is about overlearning, and so I'm wondering, is this that we can't do it? Because I would just assume.
So let me give you kind of an intuition for what I think is happening. What does it mean to learn that somebody wears glasses? I mean, look around here. Glasses come in all shapes and forms and so on. To get really high accuracy, what you really need to do is to segment the face. First of all, fine, this is the face. This is where the eyes are on the face. This is the eye, this is something around the eye. So you need actually to get really high accuracy on the task, pretty fine-grained analysis of the area around the eyes. Turns out these features enable pretty accurate race detection, and they even enable reasonably accurate gender detection. And when I describe it like this, maybe it's not surprising at all that to get high accuracy on glass detection, you're going to get yourself a race classifier just out of that.
I guess I'm asking, if we said to somebody who develops ML, look, I want you to figure out how to develop a classifier that does a really good job identifying classes without identifying race or gender.
Yeah, but that's the censoring question. That is exactly what people in censoring ask.
But I think you're saying you think that that's not possible.
I'm not saying it's not possible. I'm saying that empirically, existing techniques that we quantitatively evaluated for censoring models to prevent them from learning destroy the performance of the glass classifier. This is a purely empirical statement about existing techniques for censoring, and we did some survey of the literature, implemented these techniques. That's it.
Right, because it seemed to me that race and gender, my guess is those things are so intricately organized that you couldn't do it, but with glasses, I want to say maybe you could.
Existing techniques fail, that's all.
Maybe maybe in some way what Deirdre's asking is there a way to technically formalize an objective that is don't learn the following? And I think maybe that's an interesting technical one.
I think that's a very reasonable technical point. And there is a way, if you look at censoring literature, they do have various objectives about, that expressed in terms of mutual information between representations and so on. These are very reasonable objectives. All I can tell you today is that the techniques that people have proposed for achieving these objectives, they achieve these objectives, and the performance for the main task goes down. That's all.
What about obfuscation of the entire process?
Obfuscation of the entire process. Oh, like messing up your representation somehow. Yeah, I don't know.
Would that, I think that would formally resolve the issue that you are...
Yes, I haven't even thought about this connection ever, so.
Maybe one more question? Yeah, Lenny.
I have a simple question and then a comment, I think. So just on this whole exchange about the glasses and the race, or the glasses and the gender, is the same true about the shape and the color? Because I think that was actually the most surprising of all the examples we talked about. So that's the simple question. And the comment is that after all this discussion, maybe that suggests that the way that we have to interpret something like the GDPR purpose restriction is that it has to be about the use, the purposes in which to which you actually use the thing, because of how difficult it is to disentangle, whether in principle or in practice, to disentangle learning the thing you care about learning, and the things you might not want to learn. So it sort of, I think, guides us to, we can only interpret such restrictions in the how we actually use the box. I still want you to answer the question about the shapes and the color.
Sorry. What is the question?
Is like, can you? Okay, sorry. How do we? Why are we learning color when we're learning shapes? And
is that necessary?
Is that necessary? Yeah.
For that one, I don't know if it's necessary or not. Okay, I don't know if it's necessary or not.
Did you censor
picture and remove it?
No, wait, not.
Take the picture and remove the color, make it black and white, and see if you can still learn.
No. I don't think in that case it's necessary. Like that particular thing was in a somewhat different part of the talk. Is just showing that it extracted low-level features that also separate by color. Like that could be easily censorable. I wasn't making a statement that was uncensorable. I'm just making that if you just do learning without worrying about censoring, it's going to extract all kinds of like low-level features.
That to me was very surprising.
Why? There's a pixel level.
Nothing to do with the task, in a sense. Whereas like the glasses in the race, like you were saying, has everything to do with the task.
Nothing to do with
what?
I guess also the convolutional networks are kind of chosen to be good at like that.
I mean, they extract like features, all kinds of features. Yeah. So, but I'm not saying that that's like that part is not inherent. And by the way, like this thing, after I explained it, like why these are related, everybody's like, yeah, of course glasses are related. But it wasn't obvious to me. Maybe it's obvious to smarter people. But so on this thing about purpose, look, I mean, there are people here who are experts on exactly that kind of thing. I'm not, but. It is true that, yes, like it's one thing about regulating use, but it's very hard to regulate. It's going to be very hard to regulate if somebody were to try what is actually learned, okay? But I do feel that we will have this problem is that like somebody is going to take a model for credit scoring or something that matters to people, I know, health insurance or something, and going to look at it, okay? Some enterprising journalist is going to look at it and say, look, it's actually doing different things. Yeah.
We use credit scores for like setting car insurance prices and like a bunch of other stuff. And like the theory is that there's like something that's been learned here that is like more general than the specific task.
So and like people don't become unhappy that like
actually there's like a whole bunch of like state law about this actually. Like
see that's the problem. That's the problem. That like. It's no longer going to be about regulating use. It's going to be about regulating actual decision making. And here you have a model that's kind of doing decision making that is treating different people differently. And there's going to be like journalists and state legislators. I mean, they know, believe it or not, even less about ML than I do. And they're going to be passing laws that have no technical meaning. Like that's the risk here.
So I'm sure there are lots more comments and fodder for discussion over coffee. Let's thank Vitaly again.